Today, we are diving into something crucial for anyone managing complex projects. We are talking about risk management using a powerhouse technique, the Monte Carlo Simulation. If you're tired of missed deadlines and intend to find smarter, more robust ways to execute your projects, you are in the right place. Let's get right into it. So, I want to kick things off with a question. What if your project schedule is actually lying to you? Think about it. We have all seen that. Timeline just completely shifts into a chaotic mess. Isn't it right sometimes? A deadline gives us this false sense of security that frankly almost never exists out there in the real world of project execution. Okay then, let's dive into this. Here is our roadmap for today's discussion. First up, we'll look at the fatal flaws in the traditional scheduling methodologies. Then we'll unpack exactly how the Monte Carlo simulation works to fix it. After that, we'll uncover its specific schedule and cost application and the real danger of false precision, and finally wrap up with the real-world relevance and industry standards. Alright then, Section 1. The flaws in the traditional scheduling and why deterministic methods fail. So many meticulously planned projects just chronically run over budget or fall hopelessly behind schedule, even when our teams are strictly following the standard planning methods. You see, the root of the problem comes down to our core methodologies. Take the critical path method, or CPM. It treats activity durations and costs as a single point deterministic estimates. Basically, it implicitly assumes a level of absolute certainty that just doesn't exist in reality. Now PERT, the program evaluation and review technique, did try to improve on this. It introduced a 3-point estimation, giving us optimistic, most likely, and pessimistic scenarios alongside the beta distribution assumption. But here is the catch. PERT still eyes on a closed form approximation. Essentially, it uses rigid mathematical models and then try to just average things out. And when under pressure, those models ultimately break down. And you know where the breakdown happens. Most famously, it's a phenomenon called merge bias. As David Hewlett pointed out back in 1996, merge bias is the breakdown of scheduling accuracy that happens when multiple paths in a project networks have similar durations and merge at a single milestone. Standard scheduling tools essentially lie to us when they encounter this. They also completely fail when activities are probabilistically correlated, like say, when a task share the same limited resource or have the common risk drivers, like for instance, the weather factor. If your project network contains complex logic or conditional branching, deterministic CPM simply cannot handle that reality. So how do we fix this? Well, let's move to Section 2 and see how Monte Carlo works simulating alternate timelines. The Monte Carlo algorithm is just an incredibly clever computational powerhouse, and it operates in the basic conceptual steps. In Step 1, instead of locking in a fixed duration, you assign probability distributions to your activities. Think triangular or uniform distribution. Secondly, when you let the computer run hundreds or literally thousands of random simulations in every single iteration, it draws random duration and cost values from those distributions and recalculates your entire critical path. Finally, it outputs a probability curve. You're essentially playing out thousands of alternate timelines for your project, kind of like a multiverse to see. So the absolutely crucial point here is this major shift in our mindset. We are moving away from clinging to a single deterministic answer and moving towards a full probability distribution of a project outcome. You are no longer just guessing one exact date and crossing your fingers. You are calculating a real mathematically sound reality check. Just think about why this matters for projects you manage. It means you can finally communicate risk accurately to your stakeholders rather than desperately defending a single point deadline. Now that we have solid grasp on how it works conceptually, let's shift to the Section 3, which concerns schedule and cost application, SRA, CRA, and beyond. Because you have been probably wondering, what exact outputs can project manager actually expect when they fire up this tool? When we look at a schedule risk analysis or SRA, we see it applied to network diagrams in powerful softwares, tools like Primavera, and outputs are incredibly insightful. You get a cumulative distribution, curve the map out all possible completion dates. You get highly specific confidence level, which means you can walk into a meeting confidently, tell your sponsor, look, we have an 80% confidence level of finishing by a specific date. But best of all, you get the criticality index. This matrix shows the exact percentage of simulation trials where a specific activity landed on a critical path. It definitely solves the tricky merge bias problem that traditional CPM just couldn't detect. And this brilliantly illustrates how we handle the money side of things. Just like the schedule, we can run cost risk analysis or CRE by comparing a base estimate alongside, say, a P50 or a EET budget contingency. The simulation generates a full project cost probability distribution. This allows you to establish your contingency reserve at whatever specific confidence level your organization requires. Plus, advanced applications actually combine cost and schedule risk. They integrate them, recognizing a fundamental, undeniable truth. Schedule slippage almost always drives cost overruns through overhead and resource carrying costs. But with all this data, how do you know what to actually fix? That is where sensitivity analysis comes in, which is often visualized through these great diagrams by using regression or correlation coefficients. Monte Carlo simulation correlates your input, like those individual task duration, with your final outputs, like total project cost. It essentially applies Pareto logic to your risk management, pinpointing the vital few activities that contribute the absolutely most importantly to your overall uncertainty. This tells you exactly where to focus your risk management attention. This methodology may expand to earned value management as well. However, let's be real for a second. No tool is entirely perfect. Now it's the right time to introduce you to section 4 of this discussion, the danger of false precision academic critiques and caveats. Monte Carlo simulation can create an illusion of rigor while masking deeper reference class or estimation biases. Look, no amount of fancy computer resampling can magically correct a fundamentally biased initial estimate. This is exactly why leading scholars strongly advocate combining Monte Carlo simulation with a complementary technique like reference class for costing. We have to do this so we don't just hype up the tool while completely ignoring our own inherent blind spots. Which brings us to the classic problem of garbage in, garbage out. The validity of your Monte Carlo outputs is entirely 100% contingent on the accuracy of your input distributions. If you select your distributions poorly, well, you got distribution selection bias. This concept anchors right back to human judgment under uncertainty. If initial 3-point estimates are poorly elicited because of human anchoring or optimism bias, then highly precise looking outputs are entirely invalid. It's just bad math masquerading as a certainty. Another major pitfall to watch out for this correlation modeling. Basic naive implementation of Monte Carlo tools often just assume activity independence. But as it was emphasized previously, that the schedule risk analysis in which we ignore the correlation between activities, things like common cause risks such as sudden inflation, contractor performance issue, or extreme weather, that tends to drastically undermine the true variance of your outcomes. Think about it: if a massive storm delays task A in any project, it is probably delaying task B as well. Isn't it right? If you don't model that correlation, your simulation is going to be dangerously optimistic. So keeping those crucial caveats in mind, let's move to our final section, which is the real-world relevance and standards. Who actually uses this? Let's validate this methodology and see just how widespread its adoption really is in the industry today. Now, what's really interesting about this is how major institutional bodies formally recognizes and includes Monte Carlo simulation in their highest, most rigorous standards. The Project Management Institute, PMI, names it explicitly right there in Project Management Body of Knowledge, guide under the Quantitative Risk Analysis Process Group, and also in their practice standard for project risk management. And over on the cost side, Association for Advancement of Cost Engineering includes it directly into their recommended practices for 40R8 and 41R8 for determining contingencies. So make no mistake, this isn't some fringe academic theory. This is quite literally the gold standard of project management profession, and you see that reflected in the board cross-industry lines on integrated cost schedule risk analysis. We are talking everything from a massive construction and engineering feats to a rapid IT deployments, strictly regulated pharmaceuticals, and sprawling public infrastructure mega projects. These heavily hitting industry line on Monte Carlo simulation every day to set realistic timelines, allocate their resources intelligently, support highly rigorous go, no-go decision, and establish fully defensible contingency budgets. To sum it all up, let's look at the exact condition where this technique is most valuable. If your project involves long lead procurement activities heavily dependent upon the season or weather, constantly shifting regulatory and permitting variables, or highly independent multi-team work packages, well, then this is absolutely for you. These are the exact complex environments where single-point deterministic scheduling fails the hardest. In these settings, you're almost guaranteed to severely underestimate your true completion date and your cost risks if you don't use simulation to model that uncertainty. Which brings us to the end of the discussion. I want to leave you with a final provocative thought. We have seen exactly how traditional scheduling feels short, how Monte Carlo offers a brilliantly robust probabilistic alternative, and the absolutely critical importance of our own human biases in check when we use it. So looking at your own complex project right now, are you ready to stop guessing at the single date and start actually calculating probabilities?